Hello, in this video I introduce some basic ways to analyze your membrane simulation. To determine whether or not your membrane relaxed during simulation time, you need to use a combination of different metrics. Here I start with calculating time-dependent root mean squared deviation of atom positions from reference structure in my TPR. Calculating membrane rmsd is no different from calculating a protein rmsd, and I have a separate video where I explain how to use RMS program of GROMACS package. We can quickly visualize our plot using XMGrace. Initially, I have carried out a 100 nanosecond simulation, and based on RMSD curve, I thought that the membrane has already relaxed during 100 nanoseconds, but as you can see now, there was a certain drift after 100 nanoseconds. You can't really rely on RMSD only to determine membrane relaxation, which is why at the next step I have determined the lipid area of a membrane at each frame. Initially, I determined box X and Y dimensions. As we have NPT ensemble, box volume is not constant, and the box can actually shrink or expand during simulation. So we need to know XY plane area at each step to calculate lipid area. To actually calculate it, I am going to use a Python script. As our membrane occupies the whole XY plane, our box XY area is actually our lipid area, but we need to decompose it based on the number of lipids in each leaflet of our membrane, which is symmetrical in this case. As you can see, I have already used it to analyze 100 nanoseconds trajectory, and this is exactly how I determined that 100 nanoseconds was not enough for the membrane to relax. Now, based on this graph, roughly between 100 and 125 nanoseconds, our membrane finally relaxes, and our lipids per area reaches its normal wave-like form. It is not exactly a plateau, but mean lipid per area is roughly the same at last two intervals of trajectory, which is 100 to 150 and 150 to 200 nanoseconds. It is like wave, not plateau, because membrane in its relaxed state breathes, and it leads to changes in box XY plane area and also in lipid area. A proper mean lipid area will depend on the exact composition of your membrane. Finally, if we look at both RMSD and lipid area plots, we can see that in the end of our trajectory at 150-200 nanoseconds, there is a plateau at the RMSD curve, and at this final interval, we can also see repeats in area per lipid curve. Together, these two plots indicate that our membrane is ready for drug permeability study. And in the next video, I explain how to set up a stirred MD simulation, which is a basic technique for various enhanced sampling methods like umbrella sampling, metadynamics, and AWH. Thank you for your time.